Hello everyone, and welcome to this new and exciting session in which we shall be building our own VIT model from scratch. In the previous section, we saw how this transformer model, which previously was used for NLP tasks, could be used in computer vision with proper preparations. And so in this section, we'll see how to convert or create patches of this image and then carry out this linear projections and pass this output from those linear projections into the transformer encoder to then create or to then train an end-to-end model which learns how to say whether an input that image is that of an angry person, a happy person, or a sad.
Don't forget to subscribe and hit that notification button so you never miss amazing content like this.
Given that we'll be working with 256 by 256 images, if we have to split up these images into 16 by 16 images, then we would have 256 different images, because here if you have 256 here and then break this up here into 16 by 16, so here you have 16 pixels by 16 pixels, then you have to do the 16 times horizontally and 16 times vertically to form a 256 by 256 image. And so from here you would have 256 different patches like this one. And so what we'll use to create these patches will be this extract patches method right here. Now this extract patches takes in the image, it takes in the sizes, takes in the strides and the rates with also the pattern. So let's look at how this works. From here we have this picture here, or we have this output which will help us picture how this works. But before looking at that, let's look at its arguments. We have the sizes, or we have the images. It's a 4D tensor. We have this sizes which specifies the patch sizes. So in our case we have 16 by 16 patches, so our patch size will be 16. We also have the strides which tells us how much we should shift while creating these patches, and then we have the rates which we'll better understand with some figure. So let's now get back to this here, and then we see that we pass in the sizes of 1 3 3 1. So this list we pass in here, we got this from here. So you see, we told it must be this list where we have 1, the size row, the size column, and 1. But since the size row equals size column equals 16, then here we would have 16 by 16. Now in the case where we have 3 3, you could see here, let's have this here. You could see here, let's take this off. You could see here that we have this 3 by 3. So here, unlike with our example where we're working with 16 by 16 pixels, here they have 3 by 3 pixels. And then the next one, you have the strides 5 by 5. Now you will notice that, let's scroll this way, you will notice that when this box, or when we want to get the next patch, we shift or we go 5 steps to the right and then get this next position or this next patch right here. So you could see after shifting we get to this. So originally we had this image here, and then we're trying to get these different patches. Now the patches are what we have in stars, you can see. And then again we shift 5 steps downward, we go downward again, and then we get to this. You will see that if you can count this 1 2 3 4 5 steps, and then we get to this, and then we shift again, and so on and so forth. So that's how we obtain all this 4 patches right here. Now the next thing we'll look at will be this rates. Now the rates, again, you have this 1 and this 1, and then you specify this 2 rate values here. Now we'll look at, or we understand this 2 rate values by looking at a dilation, or by looking at a dilated convolution operation. We can see this visualization from this Medium post by Sig-Ho Tsang, where unlike with the usual convolutions, where when we having this filter which passes through the image, you see we have this 3 by 3 filter which is compact here. You see there's no spacing between each element of the filter. But with a dilated convolution, you see the spacing here. So it's kind of similar to what we will have here as let's get back to documentation. As with this, if we decide to have patches where there is some spacing between the pixels, then we could specify how much space we want with this rates right here. Now the pattern here is set to valid, and so this means that if some pattern needs to be done to match up with the extraction, then it will be done automatically. Now that said, we could copy this out, copy this simply, and then we paste it out right here. So here we have this, and then we'll call this patches. So we have this patches, and then we'll pass in our test image right here. There we go, we have test image, that's fine. And then here we have 16 by 16. Now this is the patch size, so we could do well to put that in the configuration. So we could add that to the configuration. And the strident too is 16 because we want to, let's get back here. The strident, let's see why we need the strident to be 16. Now you see that we're interested, if we have this kind of image, we are not interested in skipping this part. So we do not want to skip any parts. We want to have this, then we want to have this next. You see, this is what we want to do. Then we want to have this next and this next. Obviously there'll be padding here and here, so we'll account for the space here, and then we want to have this next, and so on and so forth. So because we want to have this, we'll make this value to be the same as this, such that when we have this 3x3 patch, we skip 3 steps and move to this next, and so on and so forth. So that said, if you want to have this kind of compact patch extraction, then you want to have the value here for the stride the same as the size. So with that, now let's configuration patch size. We have that, the 16 by 16, that's fine. And then now let's run this here. Let's run this here, this image test image. Then once that's fine, we run this, we get this error. Let's check out, it must be 4-dimensional. Okay, so what we'll do is, instead of taking this test image, we will do expand dims. So we create this extra dimension, and then we add this to the 0th axis. So we add this extra dimension, run that again. You see we have our patches. Now look at what we're gonna have when we print out the patches shape. Patches.shape, what do we get? See, we have this 16 by 16 by 768. Now let's explain why we have this. Now recall that we have a 256 by 256 by 3 image, meaning that we're going to have 3 channels like this. 256 by 256, then by 3. Now since we're dealing with patches, I think it's preferable we should take this at once. So this is 16 by 16 patch, 16 by 16 patch. Here we have this 16 by 16 patch, and then here again we have this 16 by 16 patch right here. So now we have this 3 16 by 16 patches, and then given that each and every one of those patches is 16 by 16 and 16 by 16 is 256, you'll see that if we pick a given patch, like here it says 16 by, if we pick a 16 by 16 patch, then this third dimension will be 768, simply because for each patch we have 256 pixels per channel. So here we have 16 by 16, 256 pixels, which make up this patch. Now this other one 256, and this one 256, and now if you sum this up, it gives you 768, and that's how this value is gotten. Now to plot this out, we are going to go through each and every patch. So we'll take this both vertically and horizontally. We create the subplots 16 by 16 because we will have 16 by 16 different subplots, and then for each subplot we have this image. You see here we pick ij, we pick a given patch out of this 256 patches, we pick that patch, and then we're going to reshape this, because when you pick this patch you're left with this 768 here. When you pick the patch you're left with these pixels, which have all been flattened out to this 768 dimensional vector that we calculated here. And so now what we need to do is reshape this back into a 16 by 16 by 3 pixel. Obviously 16 by 16 by 3 will give you 768. And so that's it. Let's run this now. You could always increase this figure size or reduce it depending on how you want to view this. So running this what we get is output. There we go. We see this image, which initially was compact. Now we've breaking this up into several patches. Now before we go on to create our patch encoder, which is this whole section right here, what we'll have to do is convert or reshape these patches here. So recall that in this paper, after doing this here, that's after creating these patches, we have to take each and every one of them, and this will be considered as one element of the sequence. So here we have 9 patches, and here we have 9 values which have been passed, or 9 different inputs or vectors which will be passed here. And so if we get back here, since we have 256 of this, then we'll need to reshape this such that each and every one of this will be considered as part of our whole sequence. So here we'll print out, let's reshape that. So we have patches equals reshape, and then we have the patches, and then this will give us patches, that's the batch dimension, patches shape 0, then the next one with -1, and then here we'll have 768. Now either we put -1 or we explicitly write 256. So this means that we have decided to put this now into 256 sequence length tensor. Now with this, let's print out the patches shape, and you see what that gives us. See here we have 256. Now if we put -1 here, it's going to automatically give us this 256, and that's it. So we have this. Oh, let's rerun this so we get that difference. So you see here 16 by 16 and then 256, and that's it. So each and every one of those 256 now will be passed into our transformer. Now we could modify this this plotting of the image. So let's have that, and then we'll say we have patches shape 1. So we'll take 256, and then here we have 16 by 16, and then we have simply I plus 1. Okay, so we have that. We could take off this K now. We do not need this again. Take that off, and then here we have this I here, which we now reshape into this, and this should be fine. So there we go. Let's run this again, and that's it. We get the exact same output, which is normal since we just restructured those inputs. So with this, we see that we are now set to create our patch encoder layer, and this patch encoder layer will be similar to the kinds of layers which we've been creating. So we could just copy this here, reduce that, and then paste it out here. So we'll call this our patch encoder layer. There we go. We have patch encoder and your patch encoder. So this patch encoder will be responsible for, first of all, converting our image into patches, and then carrying out the projection and adding the positional encoding. Patch encoder, that's it. And now here we have this linear projection, which we will create here. So let's call this linear projection, and we could do this with our dense layer. So we have this dense layer. Let's take that off, and then yes, we could select our hidden size dimension or embedding dimension. Now since our input is already, let's write this out here. We have inputs of let's take this off, batch dimension, or let's take the batch dimension off. We have inputs of 256 by 768 already. So this is our hidden size dimension for now, but what we could do is we could convert this into 512. So let's do just that. we could let's take 1024. Let's make the model bigger, but this is too many parameters already and it would take much time to train. So let's stay with this. Okay, so we stick with that, and let's get back to the code. We're going to specify our embedding dimension, or let's say hidden size, as is in the paper. So our hidden size, we specify the hidden size, and that's it. We're going to pass this in here. We have hidden size, there we go. And we do not need this batch norm. We have the linear projection, we have this hidden size. Okay, let's leave it this way for now. So we have this call method. We should take this input, and that will be it. We will have this calculation, which we saw already here. So we would have this patches. Let's copy this from here. Okay, so we get the input. We get this input. Now this input we'll be getting here, we wouldn't need to do this expand dims, because when training we already have the batch dimension, so we'll just have x. Let's call this in. No, let's have that as x. Okay, so we have that x, and that's fine. Then we'll do the reshaping. That's it. And then from this reshaping we'll have our output. Our output will be this patch, which has been projected to this new dimension. And so here we would have output, and it's self linear projection, which takes in the patches. Then to make this value here dynamic, we're gonna have, let's take this off, we're gonna have the patches shape -1. So this value we have here is the last dimension of our patches. So we have that, and we get that last dimension. Now that we have this set, we now ready to add up this positional embeddings we had here. So we will add this different positional embeddings here onto our linearly projected patches. We should also note that we are not going to take into consideration this class embeddings which were mentioned in the paper. As in practice, this is not really important. We have here Lucas Bayer from the Google Brain team, who says the main aim of including this was to reproduce the exact transformer network but on image patches. And so in practice, we are going to stick to this linear projections. The positional embedding now will be constructed using TensorFlow's embedding layer. So here we have positional embedding as described in the paper, embedding or encoding. And then here we have the embedding layer. Now let's check out on how this embedding layer is constructed, or first of all, what it's about. Now this embedding layer here, as described, TF-Keras layers embedding, turns positive integers into dense vectors of fixed size. Now getting back to the paper, at this point you see we have this linear projections. Here we have this linear projections which need to be added up to the position encoding, which is this once. Now the linear projection we're gonna get from here, if we include the batch dimension, we'll have an output which is batch size by number of patches. So let's call this NP, number of patches, because obviously we have this patches here, and each patch is gonna be a vector. So it's number of patches by that last dimension, which in this case is 768. So you could always fix this hidden dimension. This is our hidden dimension. Let's say batch by NP by hidden dimension. And then here, let's take this off. Let's take a batch of 1. So if we take a batch of 1, we would have 1 for the batch dimension. Then the number of patches we would have will be 256, because if we have 256 by 256 image and we break it up into 16 by 16 pixel patches, then we would have 256 different patches. So here's what we have for this one. And now with the embedding layer, what we'll be able to get will be another tensor which is like this in the output of that embedding layer. And so as we can see here, it takes these indices and then turns them into the dense vectors which we're interested in. Now the arguments we have here, the input dimension, output dimension, initializers, regularizers, as we can see here. And then we can see this example where it converts, for example, this number 4 into this 2D vector, this index 20 into this other 2D vector.
And then from this example, which we could copy out and test in our code, let's test this out. Let's add this here. So we have this which we could test out, so you see better how it works. You see the model takes as input this integer matrix by dimension by input length, and then gives this other output. Now in our case, since we're working with image data, we do not really have this vocabulary we should talk about here. And so instead of this vocabulary, we replace this by the number of patches. Now, if this were a natural language processing, then this will be the total number of words that our model can treat. And so if we could have a vocabulary of say 300,000 words, and that's what we're going to pass in as this input dimension. But as we said here, we're going to take this to be our number of patches. Now this input dimension is, as I say here, is a dimension of the dense embedding. So in this case, they put in the value 64, which we will change to 768 shortly. Now that said, we will have this model which they define. Take that off. We have this input. You see the size of this input is 32 by 10 input. There's a batch dimension, and here are the different indices. So we have this input, and then we're gonna print out the shape from here. So let's run this. There we go. You see it takes in this and then outputs this one now as a vector. So basically what we have is we could have let's take this off. What we have is we have some indices. Let's take this off. We have some indices. Let's say we have, like in this case, they have 10 indices. So we have this 7, 8, 9, 10. Okay, so here we have this 10 indices, and then we ignore the batch dimension, so we just have this 10 indices here. So this 10 indices now could be projected into its two-dimensional version, where this one will be represented by a vector. So just like the patches, so you have a patch represented by this vector, this one represented by this vector. So this is no longer represented by an index, say, let's say, because here this random values take values between 0 and 1000. So it's no more a value like say 900. So this maybe was 900, now will be converted into a vector, and the size of this vector we see here will depend on this value we set here. So you see this means that this one here now becomes a 64 dimensional vector, and so each and every one of this becomes 64 dimensional vectors. And that's why we go from this 10 to now 10 by 64, which you could see here if we ignore the batch dimension. So what we'll be doing in our case now, let's take this off. What we'll be doing in our case is we have this 768, and then here we have 256, and then the size of this input, which is going to be some random input, we'll take the size to be 32 by 256, since we have 256 patches. So we have that 256. Let's take this, we could take this off. You could check out the reason why we need the input length, the documentation, but for now we don't need that. So we'll have 32 by 256, and then we expect to have an output which is 32 by 256 now by 768. Let's modify this. Let's take one by size of 1. So let's run this, which will have 1 by 256 by 768, and you see that it would match now with this year, from the projections, or from the projections of the inputs. Now that said, let's simply copy this here. We have this layer which we're going to copy and add that here. So instead of this embeddings, we have this embeddings. There we go. And then here we'll pass in the number of patches. So here we have number of patches, and then this one is this hidden size. So here again we have our hidden size, and that's it. So now we have the hidden size we get here, and then instead of having this, we have this plus the positional encodings. So we have self.positional embedding, we could call that embedding. And then what this will take in will be an input of length number of patches. So we get back here, and then we would have embedding input, we could use the TF range, and then we have the start. We could start from 0. Here are the indices. So we have this, and then we have the limit. Our limit is going to be the number of patches, because we want to get these indices going from the 0 value to some end value, such that the length of this tensor we're going to create is going to be such that it's equal the number of patches. So our limit here is number of patches. In that sense, we could have this here. So we have number of patches already from here. So we could get self number of patches. There we go. We have number of patches. Okay, so we have our number of patches. That looks fine. And then we could make use of that here. So we have that number of patches, and then we are going to set our delta. So we have delta will take to be 1. Now obviously if we set delta to be 2, it means you're going to go from 0 to number of patches while skipping 2 steps, and that's not what we want. So we want number of patches elements in this embedding inputs. So with this now we could pass this an embedding input, and that should be fine. Okay, so we have this here, everything looks fine, and we could take this off. So now we could return our output simply. Now it should be noted that this embedding layer here is similar to the dense layer, but with the dense layer, when you have an input X, you see with the dense layer, when you have an input, let's write it here. For the dense layer, when you have an input X, that input X is multiplied by the weights, and you add the bias. So here's how we get the output. But with this embedding layer, it's a simple matrix multiplication. So when you take an input X, you multiply it by the weights, and you get the output. With that, now let's run this cell here, and then we move ahead. So we have this run, and we could delete these 2 cells now. Now to test this out, we could define patch enc. We have our patch encoder, which we've just created here. So our patch encoder, and this takes in the number of patches and hidden size. So let's specify those to 56 and 768. So we have this, and then now we could have patch encoder, and then pass in an image and see what we get as output. Here's image. We have this zeros. There we go. 1 by 256 by 256 by 3. So now when we pass an input image, we expect to get some output of shape batch size by number of patches by the hidden size, or the number of hidden units. And now that we've built this here up to the point where we have our embedded patches, let's go ahead and build this transformer encoder right here. As you can see, we start with a layer normalization, multi-head attention, and then we add this input to this output. We have a layer normalization again, then the multi-layer perceptron, and again we have this addition, and then we get the output. Now to build the code for our transformer encoder, we're gonna paste out this patch encoder here. We'll remove this. We have transformer. There we go. And then this transformer is made of a first norm layer, and then the second norm layer. Let's have this layer norm 1. It's our first norm layer. Layer normalization. There we go. That's fine. And then we have our second layer normalization layer, so we'll call this layer norm 2. Now we've defined our layer normalization layers, we could go ahead to define our multi-head attention layer. So here we have multi-head attention, and there we go. gain your multi-head attention. You could check out the documentation for this. So here in the documentation, you have the different arguments which you could pass in and the type of values which the multi-head attention takes in. So here we will specify a number of heads and the key dimension. Here this key dimension is the same as the hidden size or the number of hidden units, which in our case we fix at 768. We could also have the value dimension, drop out, and this other arguments. Now what this takes in, as you would see here, is a query, value, key, and attention mask, which we will not use here. Return attention scores, we will not do this. This training, we will not specify this. But what we'll specify will be this query and this value. And then since we're not going to specify the key, it's going to consider that the key is or rather it's going to consider that this value here is a key, so it will be the same value. That said, here we would have the number of heads. Let's take this off, multi-head attention, number of heads, and then we would also need the hidden size here. So we already have the hidden size, so we'll leave that away. Here we'll replace number of patches by number of heads. Okay, so we have our multi-head attention, number of heads, hidden size, and then the next will be the dense layers. So as you saw in this model here, you see we have, after the multi-head attention, we have layer norm 2, and then we have this MLP here, which is made of 2 dense layers. So we have our self dense 1, which is our dense layer, and then the number of units here, we'll take it to be hidden size, and then we'll specify the activation to be a JLU activation as specified in the paper. So we have JLU, and then we repeat the same process for the second dense layer. So here we have that and dense 2. Okay, so that's it. We've specified those 2 dense layers, and we now get our output. So we should have that, and then now we could go ahead and call. So before going to that, let's modify this here, transformer encoder. That's fine. The name, transformer encoder. There we go. That should be fine. Okay, so we building our transformer encoder layer already, and now we set to pass this inputs into these different layers. We have our input here X. There we go. We have X. Let's take this off, and then X gets into the layer norm 1. So we have our output X equals layer norm 1, which takes in this X here, takes our input X, and then our outputs this. We could call this in, and then we have this input. We have our input, which gets in here and then produces an output X, and then from here we get into the multi-head attention layer. So we have X again. This is multi-head attention, and this takes in X. So now we have this input which gets here, gives this output. This output gets into this multi-head and gives this output. Now that we've had this, remember from the paper that we have this addition to do. So we have this add layer, which we need to specify here, because after this output got into the multi-head, we got this output which now needs to be added to this input from the patches. So we need to create this link here. So that said, getting back to the code, we have X now, which is add, and this add will take in this X and the input. Then from here again, we take this and pass into our layer norm. So now we'll call this, let's call this X1, because we'll need this X1 again, so we can't just be working with X. You'll understand shortly why we need this X1. So we have this, and we have your X1. Okay, so we have that, and that's fine. Everything looks fine. Then from here, we take this and pass, or take this output X1 and pass into our layer norm 2. So we call this layer norm 2. That's it. And then this takes in our X1, produces output X1. Then from here, we take this and pass into our dense layers. So we have this x1, which is equal dense 1, and this takes in x1, and again we have x1 which takes in dense 2, which takes x1 which is gotten from dense 2, which takes in x1. And now let's say this produces an output x2. Remember, this is like our final output, so let's call this output, or let's call this output. Okay, so that's our output right there. Now let's do this. Then for this output, again we're gonna do this addition. Recall from the paper, you see, after doing this addition you get an output. We get this output, that we take this output from here and add onto this. That's why you see we had to create x1 for this and then x2 for this. So let's get back to our code. We have that, and then here we have our output now, which is equal add, that's it, and then it takes in our output and this x1 here, or rather this x1 after this addition. So we need to have this as x2. So let's change this to x2 so we could make use of this now in this addition, because if we have this, if we maintain this to be x1, then the value we'll be getting here would be this final x1 we got here, and that's not what we want. What we want is this output from here, so that's why we had to change this variable name. So we have x2, this takes an x1, and then that's it. So from here now we take this output and add it to this x1. There we go, we have that x1, and we get now our output. So we could close this up, and that's fine. So we return our output, and we have our transformer encoder right here. Now we could go ahead and test this. So we have our transformer encoder, number of heads, hidden size, that's fine. And then we also have this input right here. Recall that the input or the patches take this form. So let's run this and see what we get. We're getting an error from this. Yeah, this is logical because we need to pass in at least 2 inputs. So here, if you recall from this here, from multi-head attention, you see this, we have this 2 which must be passed in. Then this key is optional, this one optional, and all this rest optional. So we must pass at least this 2. So that's set. Let's get back and modify that. So in this multi-head attention, we have this, and then we have x1. So that's fine. So now we have that. Let's run this again and see what we get. You see, that's fine. You see, we get exactly what we expect. So there's the kind of input we get, and here's our output after going through the transformer encoder. Now, although this works, make sure that you check your work or check this code and be sure that everything is working as it's supposed to be. So be sure that you pass in the right inputs and get the right outputs, and so that you get the exact output you ought to get, and not some outputs different from what you're supposed to have. So that's it. We have our transformer encoder, and now we'll head on to building our VIT model. So here we would have our VIT model. Let's get back up here. Let's copy this, the ResNet from here, complete network. We had this, so we just simply copy the same structure and then paste it out here. Now, although there's not much difference, we'll just, the main difference here is that we will have this model instead of layer. So here we have a model, and then here we'll call this VIT. So here's our VIT model, our vision transformer model, and then here we'll change this. We have the vision transformer, and we'll call this our vision transformer. Vision transformer. That's it. Okay, so there we go. We could take this off. Take this off, and all this off. Then we build it in such a way that it takes in the number of heads, the hidden size, then from this patch encoder, the number of patches. So we just need number of heads, hidden size, and number of patches. So with that, we would specify number of heads, there we go, hidden size, and then number of patches. Okay, so we have that, and then here we would have our patch encoder, which will be defined. So we have patch encoder, and this patch encoder which we having right here is simply what we created already. So we just have patch encoder, and what does this take? So we get back here and we look at this format, see number of patches and hidden size. So that's why it's important for you to test this as you go on. So since we've tested this, we show that this works when you pass in an input image. So your patch encoder, number of heads and hidden size, or rather number of patches and hidden size. So we have number of patches, then the hidden size, which we'll get from here. Now we have this patch encoder. We have our transformer encoders. Recall that we have several transformers here. See, we have L transformer encoders. So we get back here, and then we define this transformer. Let's call it trans encoders. Okay, so this transformer encoders will be a list made of different layers, and the length of this list will depend on the number of layers. So we have here number of layers, and then what we'll do is we'll say for underscore in this number of layers, or rather in range number of layers. See, we are then going to define the transformer encoder. So we have transformer encoder, so we have the separate transformer encoders, and then we'll specify number of heads and hidden size. So here again we have number of heads, and then we have the hidden size. The input gets through this patch encoder. So here we have our patch encoder. That is it this way. We have X, let's call this input. So here we have input, and this passes through the patch encoder, and then produces the output X. Then once we have this output X, what we are going to do is we are going to loop through, or we're going to go through each and every transformer encoder layer. So here we have for I in range self dot number of layers. Let's define this here. Number of layers equal this number of layers from here. So we've set our number of layers, and then we take this in here. So now we're gonna go through this, and then what we'll be doing is we'll be having this X, which is gonna be the output from this our transformer encoder layers. So we have trans encoders I, which takes in the different inputs X. So we'll do this for number of layers times, and then for each of this we have trans encoders as we've defined already here, and we pick the specific transformer encoder. Now once we get the output from here, you see, once we get our output from here, we'll now obtain an output which we will flatten. So from here we'll say X equal, we'll flatten this out, taking X, and then from this we'll have this MLP block right here. Let's get back here. We have MLP block here. Okay, so we have this MLP block right here. That's after this. Now on the paper, what they had done was, since they had this class token, they picked this last, or rather they picked this first output here. So this means that if we have, let's take from here, if we have an output batch size 1, let's take this off, 1 by 256 by 768, then out of this 256 here, or 257, because they will have this additional, so out of this 257 we'll pick out only one from here, and so we'll be left with that one which has 768 hidden units. So basically this will be like having 1 by 768 output. But now since we're taking all this into consideration, we'll just flatten this out and then pass this through our MLP head right here. So that's it. Let's get back to the code. We flatten this out, and then we specify the dense layers which make up the MLP head. So we have dense 1, dense layer. This dense layer has certain number of units. Let's say 1,000, or let's give this dense units here. Let's have it as this argument. So we have number of dense units. Okay, so we have our number of dense units there. Let's specify this number of dense units, and then we have the GELU activation, CFNN GELU. Okay, so we have that for dense 1, and now we should have, or we should write this code for dense 2. So we have now dense 2, and then here same number of dense units. You could always modify this, and that's it. Next, from here we have x equal dense 1. That's it, dense 1. This is self. Okay, so here we have dense 1, which takes an x, and then dense 2, which takes an x. Now our final output dense layer has to consider the number of classes. So just as what we have been doing so far in this course, let's take this complete block here. So far what we've been doing is we always ensure that our output dense layer has the number of classes, number of units in this output. So here we would simply copy this, scroll down back to our code, and put this right here. So that's it. So let's call this dense 3, dense, and that should be fine. Okay, so here we have dense. Take this off. That's fine. We have that. Now let's run this. Should be fine. Let's go ahead and test this. So here we have our VIT model, and we'll define VIT equals VIT, and the parameters, those arguments here, number of heads, hidden size, all of this, we're going to define this just down here. Scroll down and then define this here. Okay, so we have now this number of heads. We say 8 heads, hidden size 768, number of patches 256, the number of layers, let's say 4 layers, the number of dense units, let's say 1024. Okay, so there we go. We have our VIT, and then this VIT now we pass in this input to 1 by 256 by 256 by 3, and we should get reasonable output. We could print out the summary, so VIT summary, and we could check out this model. So you see here we have 283 million different parameters for VIT model. Now let's reduce this. We could say 4 heads, just 2 layers, and then this number of dense units here we could take 128. Now let's run this again, and there we go. You see the 2 layers, you see the patch encoder, and then you see the dense layers which follow this transformer encoder layers. So now we have this model. We'll change this to the batch size. So we have configuration and then batch size. Now the reason why we're doing this is because when we're training, our batch size is going to be known, so we don't want to have this here like that. So with that, now we run this again and run this summary. Yeah, we need to change this to 32. You see, when we change this, it doesn't work. So here we have 32, same as our batch size. That's it. And now we can go ahead to compile and train our model. Our model and our training, note that we wouldn't get the best results because obviously the VITs need very large data sets or even extra large data sets to perform as well as a ConfNet. And so when working with the VITs, generally we want to train on a very, very large data set, and then later on fine tune on a smaller data set. Towards the end of the epoch, we still get this error, and the source of this error is the fact that since we've fixed the batch size, that's if you get back up here in our training, if you look at this here, we fixed this. And so since this isn't dynamic, now we have a data set which has been broken down into batches of 32, and now towards the end you may have a batch of, say for example, 8. Obviously, because the data set isn't necessarily divisible by 32. That is, the number of elements you have isn't necessarily divisible by 32, and so you will have a remainder. And so when you have this remainder and that you fixed this here, you should get an error, because now you've told the model to always use at this position a value of 32. So to avoid that, instead of doing the patches shape, we're gonna do tf.shape. So with tf.shape, before we had patches, we got the shape, and that was it. But now we instead using tf.shape, so we call in the shape method from TensorFlow, and then here we're gonna pass in our patches. So once we have those, once we have our patches passed in, we now select this batch dimension, and that should be it. So let's run this again. You would see that even from here we could modify this. We could put 32 and it'll still work fine. Okay, let's say 2. So with that, now let's go ahead and compile and then restart the training. The model is training, and as you could see, it starts to stagnate around this 44.4% accuracy and 44.16% validation accuracy. In the next section, we will fine-tune a VIT which has been trained on a very large data set.